Hello, this is Shankar from System-Based Labs. I've worked across regulated environments and medical imaging platforms, and I'd like to share some practical insights from that experience. Today, we are going to explore a very important topic, how validating a machine learning model is different from traditional system validation, and how to defend it in real-world audits. Let's start simple. In traditional system validation, we validate against predefined logic. We know the inputs, we know the expected outputs, and we verify whether the system behaves as expected. Same input gives the same output. This is deterministic behavior. So, validation becomes straightforward. Compare expected versus actual results. Now compare that with machine learning systems. Machine learning models are non-deterministic. Their behavior is not defined by rules, but learned from data. So instead of validating fixed outputs, we evaluate performance across data sets. This is the fundamental shift. Now let's go one level deeper. Even in traditional systems, data is involved, but the logic is fixed. The system does not learn from data. It executes predefined rules. In contrast, ML systems are highly data dependent. The quality, diversity, and representativeness of data directly affect system behavior. So validation must now focus on dataset quality and traceability, model performance metrics like sensitivity and specificity, and risks such as bias and model drift. We are no longer validating just logic. We are validating behavior driven by data. In traditional validation, once a system meets predefined criteria, it can be qualified. It becomes a validated system. Revalidation happens only when changes occur, so it is largely a point-in-time activity. But in machine learning systems, this changes completely. The model depends not just on initial data, but on ongoing data. As data evolves, model behavior can change, performance can degrade. This is known as model drift. So even if a model is validated today, it may not perform the same tomorrow. This is especially important for adaptive models. So validation is no longer a one-time activity. It becomes an ongoing process. Continuous monitoring, periodic revalidation, constant awareness of data changes. Now let's take it further. Validation is not just sequential. It is continuous. Documentation is not a final step. If you document at the end, you are reconstructing history. And in regulated environments, that creates audit risk. So documentation must happen while defining criteria and executing tests, while validating data sets and while integrating into workflows. Documentation is part of validation, not separate from it. My background includes working with legacy systems, COBOL, CICS, Fortran, where documentation is often minimal. In those systems, you don't rely only on documentation. You analyze behavior. And I apply the same thinking to ML systems. Because ML models are black boxes. Their logic is not explicitly written, it is learned. So I don't just ask, does the model work? I ask, where does it fail? Under what conditions does it break? What patterns drive its decisions? I probe inputs, I analyze outputs, I study failure patterns. In traditional systems, you read the logic. In ML systems, you infer the logic. That is where real validation happens. Now let's move into practical audit scenarios. This is where validation thinking is truly tested. Sometimes auditors want to understand how we manage validation beyond the initial phase. In our approach, revalidation is triggered by changes in the model, shifts in data distribution, or updates in the environment, or any observed performance degradation. Auditors often ask how we ensure dataset quality in the organization. We address this through periodic validation of source traceability, labeling accuracy, completeness, and representativeness. This ensures that the data reflects real-world conditions and does not introduce bias into the model. They may also probe into how we detect model drift. In practice, we monitor performance metrics over time and compare them against baselines. Any deviation from expected performance signals potential drift and triggers further investigation and revalidation. Now here's where most people fail in audits. They say the system is validated, and then later they say model behavior changes. That creates a contradiction. The correct way to think about this is the system is validated at a point in time based on defined criteria, and it is maintained in a validated state through continuous monitoring and controlled revalidation. This single structure brings consistency to your answers, and more importantly, it protects you in almost every audit scenario. Let me leave you with this. Traditional systems validate logic. Machine learning systems validate behavior over time. Validation is not about proving a system works. It is about understanding where it might fail and ensuring that failure never reaches the real world. This is Shankar from System-Based Labs. See you on the next training session. Goodbye for now.